Good afternoon, students. Today we are going to deal with the revision class regarding your midterm syllabus. Okay. So in that, I hope I already explained the solid state solution and chemical kinetics. Okay. So before interest, so I'll go with the inorganic chemistry chapter. That is D and F block element I explained. Okay. Another one is the P block element. Very important one day I discuss. P block element and G and F block element. So in that P block element, the important one is Aver's process. Okay. So in that Aver's process, flow chart is there. Okay. So what is that flow chart? Listen, your inlet values are there. H1, H2, N2, inlet values. Okay. Next. And no matter how you are writing the flowchart, but you have to represent each and every steps. And what are these compressor? Okay, here it is compressor. Here it is catalytic converter. Okay, compressor, catalytic converter. Next. Here it is condenser. This one is what? Liquid ammonia. And this one is again connected to what? Pump. This is the flowchart. No matter I am telling this is the way you have to write, you have to even connect with this. Okay. So if compressor means here 2000 atmospheric pressure will be present. So these N2 and H2 gas are introduced here and they are compressed under the pressure 2000 atmospheric pressure, and here catalytic converter is there. What is the catalytic converter here means iron is present as a catalyst and molybdenum is catalytic promoter, and K2O and Al2O3 are used to maintain equilibrium. Okay, so these are all present in this catalytic converter, and here at the same time you are going to have 700 Kelvin temperature, that is 500 degrees Celsius. Understand? Next year condenser is there. Here the temperature increases means, of course, they are in highly gaseous state. Then the mix up takes place here, mixing up of H0 into gas. So here NH3 is formed. So this NH3 is greater in temperature, that is condensed here. Water condenser or air cooled condenser, whatever it may be. Okay. Next, that liquid ammonia is collected here. The unreacted N2 and H2 gas again pumped into this compressor. Here the direction is like this, from this to this, and this. Again, these unreacted gases passes through this pump and again enter into this compressor, and the reaction repeats. This is the flow chart. Next, what is the reaction or the reaction condition? So listen, N2 plus H2 gives rise to NH3. This is the reaction takes place. What is the condition here for the reaction? So iron as a catalyst, molybdenum as a catalytic indicator, catalytic promoter, K2 and Al2O3 as a equilibrium constant, 700 Kelvin temperature, 200 atmospheric pressure. This is the reaction condition. Here, balance the reaction. This is 3 moles, this is 2 moles. Okay, next, what are the condition here? Temperature must be 700 Kelvin. Next, pressure 200 atmospheric pressure. Next, iron as a catalyst and molybdenum as catalytic promoter. Understand? So these are the conditions for the preparation of ammonia by Ebers process. Understood? Okay. So next one is manufacture of nitric acid. Next one is manufacture of nitric acid by Ostwald's process. Okay, so students, in this only steps are there: step 1, step 2, step 3. There is no flow chart and all. So in step 1, what happens? Ammonia reacts with air in presence of platinum or rhodium as catalyst. Platinum or rhodium as catalyst. Okay, so first step is with temperature 500 Kelvin and 9 bar pressure. This is the condition. Listen, ammonia reacts with oxygen in presence of platinum or rhodium as a catalyst and 500 Kelvin temperature and 9 bar pressure. These are the reacting species. What happened here? It formed NO and H2O. We have to balance this. So here 4 moles you take, 4 moles of NO. This is 2H2O. That is 3. Okay. Second step. Okay. Second step is again NO form is reacts with excess air. Excess air nothing but that oxygen. This is NO plus O2. This is 2 moles gives rise to 2NO2. This is the second step. Step 3. Okay. So this NO2 is diluted with water or reacts with water. So you take NO2 plus H2O gives rise to HNO3. You take 2 moles. HNO3 plus NO. Plus here. So this is the reaction. Okay, listen students. This NO which is generated here again follows second step. NO again reacts with excess of water, forming water. Again it is separated. The NO formed here is recycled. These are the steps involved in preparation of nitric acid by Ostwald's process. If you write this much, you get 3 marks. Okay. So the next one is, of course, I told you, you have to practice the reaction of this nitric acid in concentrated solution and dilute solution. Okay. So always in concentration it liberates NO2, in dilute it liberates N2O or NO. The difference you understand. Okay. And also anomalous behavior is there, reason for anomalous behavior. Only four reasons are there. That is, say, smaller the size, greater the electronegativity, greater ionization energy, and absence of d orbital. Okay, these are the anomalous behavior. Just go through the videos, and this is very important, so I explain you. So I go to the next chapter, D and F block element. So students, why I am not telling this contact process means because the contact process, the preparation of sulfuric acid by contact process is removed from your syllabus. Understood? So that's why I am not explaining it. So next here, D and F block. Of course, in this the preparation of K2Cr2 and KMnO4 and their properties are there. That is also removed in your syllabus. So I directly explain with the properties of D and F block elements. So in that properties, first one is electronic configuration. Electronic configuration. Okay. So students, in this electronic configuration, you know the general electronic configuration of d orbital is n minus 1, d1 to 10, ns2 for d orbital. For f orbital, it is n minus 2, f1 to 14, nd 0 to 1. N minus 1d is 0 to 1, n is 2. This is the general electronic configuration for F block. Okay, so in this, the very important thing in this you have to remember is the atomic structure of chromium and copper. Here it is gadolinium. This is very important. I gave the general formula. This is the 4D series. You just remember the atomic number of gadolinium is 64. Here it is 24. Here it is 29. You just try the electronic configuration by yourself, which are very important for 1 month. Okay. So next we comes to atomic size. The students as they know the atomic size of the D block elements or whatever it may be decreases from left to right or along the period they decrease. The same follows in the D block element. But so in the D block element 4 series are there: 3D, 4D, 5D, and 60 series. Okay, so listen here. After 4D, we know that 4f orbital will come. This 4f orbital will come before 5d orbital. You know that. Okay. So remember here, 4d is there, 4f is there, 5d is there. But we are studying about what? Atomic size of the d orbital. What happens to their atomic size? So here, 4d orbital is there, 5d orbital is there. Along the group, along the period, size decreases, it follows the same thing. But along the group, size increases. That means, 3D orbital size must be less than 4D orbital size, must be less than 5D orbital size, must be less than 6D orbital size. Because here 3, 4, 5, 6 means extra shell is going to be added. But here, instead of this order, what happens? This 3D orbital, of course, it is less than 4D, but 4D is approximately equal to 5D, which is approximately equal to 60. Understand? 4D orbital is less than 5D. So 3D orbital obviously less than 4D. That is correct. But in between 4D and 5D, they are approximately equal. Similar radii, they have atomic radii. So what is the reason for this is Lanthanoid contraction. Lanthanoid contraction. Okay. Similarly, 5D and 60 series are there. So these are having same similar sizes because of what? Actinide contraction. What is this Lanthanoid and actinide contraction? Remember here, when we write the electronic configuration, we used to take 5s, 4f, 5d, 6s, 4f, 5d, 60. This is the order. Okay, another one is 7f, 5f, 60, 70. So this is the electronic configuration of 4f series. And 5f series, this is the order. After 6s 4f will come, after 4f 5d will come, after 5d 6p will come. You just go through the electronic configuration list what I gave in the before video. Okay. So students here, after 1s 2s 2p 3s 3p you know, after 3p 4s, next 3d, next 4p. Similarly 5f 5s 4d 5p. Next 6s 4f 5d 6p. 7s 5f 6d 7p. That is the order. Okay. So in this, what happens? Listen. Here I am telling 3d series is there, 4d series is there, 5d series is there. Here of course 3d is better than here I write 1s is there, next 2s 2p, next 3s 3p, next 4s 3d 4p, next 5s 4d 5d, next 6s 4f 5d 6p. Here. So listen here, after 3d and 4d the continuous orbitals are s and p orbitals. After d orbitals directly p orbital will go. That is in the next energy level. Okay, so it follows the same thing. So that's why 3d orbital has the least size than 4d orbital. That is correct. Nothing is different in it. But here in 4d and 5d, why it is greater in smaller, equal in size? Why? Because of this 4f orbital and 5f orbital involvement. F block elements are involving in between s and d orbital. So 4f orbitals are called as what? Lanthanoids. 5f orbitals are called as actinoids. Okay, contraction means decrease in size. So why it is called as lanthanoid contraction means, so because students, here 4f orbitals are involved in the decrease of the size. Here why it is called as actinoid contraction means actinoids are going to involved in the decrease of the size. How it is decreased? What is the reason? Listen, 6s is there, 4f is there, 5d 6p. Here listen, which is the inner orbital? N minus 2, F1 to 14. This is the inner orbital. Later this is the d orbital. So here 5d shell decreases in size. Why? Because you know number of electron increases in the shell means size decreases. Here I say 1s, 2s, 3s, 4s. Okay? Here 1s, 2s, 3s, 4s. So listen here. So 1s to orbital, 2s to 2p, 3s to 3p, 3d, 4s to 4p, 4. So here next one is 5d. So 4f is here, 5d is here. So here in the 5d subshell, before enter into the 5d orbital, we need to fill up 4f. Here the number of electron goes on increases means what happens? The size moving towards the nucleus means size decreases, effective nuclear charge increases. That's why in 4d and 5d, here listen, in 4d series what happened here? So here s orbital 1s, 2s 2p, 3s 3p 3d, 4s 4p. So listen, 1, 2, 3, 4 subshells are there. Here 1, 2, 3, 4, 5 subshells. Sorry, main shells are there. Obviously, this size is more compared to this 5d orbital. And at the same time, what is the reason for that? Here listen, inner orbital consists of extra 14 electrons here. Extra 14 electrons means effective nuclear charge increases. That's why due to the increase in the effective nuclear charge or the screening effect of this inner orbital or inert pair effect of this 4f orbital results in decrease in size of 5d series. That's why that 4d and 5d series now same size. So how the question will ask? So listen, zirconium and osmium. Zirconium means 4d series element, osmium means 5d series element. So zirconium and osmium size are same, similar, give reason because of the lanthanoid contraction. And they ask what is the consequences due to this contraction. What happens? What happens means due to this the size of the d block elements, that is 4d and 5d series, decreases gradually. Understand? Means the effective nuclear charge increases, the screening effect decreases. Here, the greater inert wear effect is observed. Understand? This is what atomic cell. So next one is their magnetic property and their color. Okay, so everything is based on what? Oxidation state, everything, catalytic property. So I'll go with oxidation state here. Okay, so these elements have the configuration Ns2, N-1D, N-1D, 1 to 10, Ns3. You know that students, from the loss of this outermost electron, they exhibit +2 oxidation state, that is lower oxidation state. And at the same time, N-1D subshell means they are exhibiting variable oxidation state. That is higher oxidation state. So now remember, the oxidation state may be equal to number of unpaired electrons. Okay, number of unpaired electrons. Oxidation state is equal to vanadium, chromium, manganese, iron, cobalt, nickel, copper. So I'll take the last configuration for all. This is +2. Atomic number is 23, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So remember students, I will consider only these two. Chromium is 24 with electronic configuration. This is R1, 3D4, 4s2. And this manganese, that is R1, 3D5, 4s2. Two configurations are there, I will consider it. So listen, this chromium box diagram is 1, 2, 3, 4, 5 I will take, and this one is manganese, 1, 2, 3, 4. This is chromium, this is manganese. So students, here you know this to attain stable configuration, this configuration changes to 3D5, 4s1 to maintain attachment. But for this, listen, if it is in +2 oxidation state, both +2 oxidation state means these two electrons is going to remove these two electrons, Cr +2 and Mn +2. So this will consist of this 4 electron, this will consist of 5 electron in Mn +2 configuration. Understood? So here it may attain Mn +3 also, then 1 electron loses for Mn +3, and Mn +4 means another electron, Mn +5 means another electron, Mn +6 means another electron, Mn +7 means another electron. So I will give the example for +2 and +7 oxidation state. You know stable compound MnO and as well as Mn2 or Kmn4. So students, you may check this and this. So here Mn is in my +2 oxidation state, here Mn is in +7 oxidation state. Means this is also stable, this is also stable. That tells about what? This Mn may attain variable oxidation state. What is the reason for that variable oxidation state? Means the vacant presence of vacant orbitals. Okay? Orbitals are there and they are vacant. Not this d orbital. Because listen, what is its electronic configuration? After 3d, 4s is there. 4s, 4p, 4d. Here p orbital, s orbital is there. P orbital is there. In the same subshell, 5 d orbitals also available. So because of the availability of this vacant d orbital, they are in higher oxidation state. That is one reason. And another one is catalytic property. What is the reason for that catalytic property? Why they act as catalyst? Because they give very much surface area for the absorption of gaseous atoms. For example, because of the presence of this vacant d orbitals and as well as the ability to attain maximum oxidation, so the variable oxidation state results in the maximum catalytic property of this D and F block elements. Understood? So these D and F block elements are highly catalytic property in nature. The reason, two reasons for their catalytic properties. One, the availability of vacant d orbital, and second, they have the capacity to attain variable oxidation state. So remember students, from using this configuration only, we can calculate the magnetic property also. Okay, which one is paramagnetic, which one is diamagnetic. Listen here, if it is like this, unpaired single electrons are there, then they are paramagnetic. If paired electrons are there, then they are diamagnetic. Example for paired I give Cu plus 1 configuration you take. Cu atomic number is 29, plus 1 means it is 28. Electronic configuration is 3d9, 4s2. After that it becomes 3. So here, if you fill up the electrons, it is completely paired. And you take Zn plus 2. So Zn plus 2, its atomic number is 30, the total number of electrons is 28. So that is 3d10, 4s2, 2 electron loses here, then become 3d10, 4s2. So here also, it is completely filled. So that means what? It is diamagnetic. If the electrons are completely magnetic, this is what we are going to explain about the character, paramagnetic character and diamagnetic character. Understood? So students listen here. From this unpaired electron, we can calculate magnetic moment. So that is, formula is square root of n into n plus 2 more magneton. So what is this n value? That is the unpaired electron value. So here listen, 1, 2, 3, 4 electrons are there. So n is equal to 4, it becomes, you take square root of 4 into 4 plus 2, then you will get 4, 6 are 24, approximately 4.9 more magneton you will get. So here if you consider, n value become 5. So then here square root of 5 into 5 plus 2. That is square root of 35. So this is 5.9 something or 5.8 something. Understood? So this is how you are going to calculate that magnetic moment value by this. So students, they may ask magnetic moment for Mn plus 3 also. Mn plus that is colorless. If n only electron is left, then it is colored. We don't know. Based on their DD transition, they possess certain color. Understood? And this is all about what? The properties of the D and F block elements. So in that students, you have to remember what is Lanthanoid contraction, what is its consequences, and these properties, especially catalytic, magnetic, and oxidation state, and then what is the reason for the color, okay, and also difference between the Lanthanoid and actinide contraction. You just go through them, okay. And remember, in P block elements, I told you the different reactions, that is variable reactions. The reactions which involve concentrated nitric acid and concentrated dilute nitric acid, and excess of ammonia and excess of chlorine. Such a type of comparative reactions you have to practice. That is very, very important. Okay. So next we will go through which one? That organic chemistry. So in that organic chemistry, that is alloalkanes and alloarenes are there. Okay, so in that, as I told you, nomenclature is there and also classification is there. So in that classification, three types is there. One is primary alcohol, secondary alcohol and tertiary alcohol. Primary alcohol means you take CX bond is there. Here also secondary means CX bond, secondary means CX bond, third tertiary means CX bond. If the halogen which is attached to the carbon, that is further attached to another carbon like this. So this is what? which is attached to another carbon, then that is primary. So the halogen which is attached to which, sorry, the halogen to which the carbon atom is bonded, or the halogen which is bonded to the carbon atom, it is further attached to R group, then it is secondary. So then it is attached to the 3R group, then it is tertiary. This is one type of classification. Next, second one. So based on an sp3 hybridized carbon atom next to the sp2. For example, CH2 double bond, CH single bond, CH2 X. This is sp3 hybridized carbon. This is sp2 hybridized. This type is allyl link. So instead of this benzene, instead of this CH2 group, assume CH2X is there. So to this benzene ring is attached. To this benzene ring is attached. So then it is benzyl link. Okay. Next, instead of this sp3 hybridized carbon, if it is directly attached to sp2 hybridized carbon atom, so then it is vinyl link. If this group must be a benzene ring, if it is a benzene ring, then it is aryl link. Or aryl halide, you may take vinyl halide or aryl halide. Okay, this is a simple classification. Primary, secondary version, allyl is benzylic, and this vinyl halide, this one is aryl. Okay, next one is nomenclature. The nomenclature always follows alloalkanes. Remember this. If you remember this, means chloropentane, chlorobutane, chloromethane. Okay, if parent change is like that, if any substitutes are there like bromethane, okay, okay. 2-chloro, 2-methyl propane. Understood? Like that. So the follows the name alloalkane. Nomenclature is also important. So next, as we come to preparation and also chemical property, in these alloalkanes and alloarenes, the chemical properties are very important as they consist of mechanism. So I'll go with the mechanism, students. They undergoes what? Nucleophilic substitution reaction. In that SN1 is there and SN2 is there. So I'll go with the SN1 reaction. What is the main reaction? Listen here. CH3 thrice COH or CBr. Tertiary butyl bromide. The structure is like this. CH3, CH3 to the halogen which is attached to the carbon atom, that is further attached to 3 carbon atom, 3R group, that is tertiary, and 4 carbon atoms are there, butyl, and it is bromide. Tertiary butyl bromide. Understand? So this structure, when it reacts with any alkali, KOH you take, it forms CH3 thrice COH plus KBr. This is the main reaction, and this reaction taking place in steps. So first one is step 1, formation of carbocation. Listen here. So this carbocation is there, that is CH3, 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 Br. Okay. So here what happens? Here the breaking of the bond means the electron move towards this. Bromine is detaches from this with the electron of the carbon. Then it forms CH3, CH3, CH3 plus Br minus. Okay, so students, this step is slow step and it is the rate determining step. Okay, what happens here? Formation of a carbocation. How it happens? Electrolytic bond cleavage takes place in between the C and Br bond. Then they form carbocation. Then you take carbocation. Here you write tertiary butyl bromide. Okay, so students, this molecule is planar. Planar means the structure is like this: CH3, CH3, CH3 plus. This is in planar because here this carbon atom is sp2 hybridized. sp2 hybridized means that is planar molecule. Its structure is planar. So then what happens? Here you take step 2. Attack of nucleophile. Attack of nucleophile. So here what happens? Take this planar structure CH3, CH3, CH3. Okay. So here addition of this nucleophile. Which one is the nucleophile here? OH minus. So when this OH minus is approaches this carbon, then what happens? Listen here. They form a mixture of compounds. So the CH3, CH3, CH3. Here OH may be attached here if it is attacking from the front side. Or there may be a chance of this OH attacking from the back side. So then they form plus C, CH3, 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 OH. So students, here a mixture of two compounds will form. So this compound is called as enantiomer. Okay, what are these enantiomers? Enantiomers means they are the equimolar mixture of non-superimposable mirror images. Okay, equimolar mixture you won't take. So this is the mirror image. How? So listen, if we take this and we keep it here, then we won't, it cannot be superimposed. And of course, if we keep mirror here, OH is here, CH3 is here, this CH3 is here. This is exactly look like a mirror image. Understand? So that's why. So these are in this we will get the mixture of mirror images, that is specially non-superimposable mirror images. Those are called as what? Enantiomers. Okay? And listen here. If OH is there, so this is the major part. This one. This one is the minor. Means not minor, not major. Mixture is there. In that mixture, this is in major concentration, that is in minor concentration. Both are present. This must be as how much? It must be 55. That must be 45. Slightly excess, not more than. This must be 51%. This must be 49%. Only slightly excess mixture will be there. Understood? So at that time, so these enantiomers will form. So that's why students, here where the nucleophile is detached, at the same time the nucleophile is attached. That means retention of configuration takes place. If you write this much, don't write this and this. If you write this much, you'll get 2 marks. Sorry, not 3 marks. 3 marks important question it is. Okay? So the next one is SN2 mechanism. Next one is SN2 mechanism. So why it is called as SN2 mechanism? Means this it only why it is called as SN1? It is unimolecular. It depends only on this carbocation. How many carbocation is produced? That much of product is going to form. Understood? So here tertiary butyl bromide is there. So this complete reactions depend upon what? The tertiary butyl bromide compound. So the next one is SN2 mechanism. Why it is called as 2? So because it depends on both nucleophile as well as the alkyl. Understood? So listen, it is a single step reaction. It is a single step reaction, right? So we are taking methyl bromide here. If it reacts with KOH, form CH3OH plus KBr. This is the reaction. This reaction taking place in a mechanism. So what is that mechanism? So listen. Initially, this CH3 is there and Br is there. Okay. So to this at the same time OH is attached. Okay. So at this time what happens? They form a transition state. So I write the CH3 like CHHH here and Br here. So this is in this structure. Structure like this. So students, this is the structure. So here what happens when CH3 Br is there, OH minus is there, at the same time here one breakage will take place. This is attacking towards this side. One breaking will take place. At the same time, one making will. So this state is called as transition state. What is this transition state? The state where the simultaneously breaking of the bond and the making of the bond takes place. And the next step is it completely detaches. That means this is the structure. H, and here OH is attached, and here Br is detached. Understand? So students here listen. Initially, the structure is, I'll take here. H. Initially, here this is the configuration. At the end, this is the configuration. Means here Br is present here. Here OH is present in the opposite side. Here inversion of configuration takes place. It is inversion of configuration. Remember students, SN1 reaction favors like tertiary is greater than secondary, greater than primary, greater than alkyl. And this alkyl favors SN2 first. So this is the primary, alkyl greater than primary, greater than secondary, greater than tertiary. This is the order of the stability or a favorable condition for a SN1 and SN2 mechanism. Understand? Both are important for 2 months. So the next one, students. Listen. Woods reaction. Woods. Repeat reaction. Okay. Next. Woods. Fitting reaction. Okay. Consider here only alkyl groups are CH3X plus Na 2 moles plus XCH3. Here these two R groups are what? Is a general formula. Of course, Rx plus 2Na plus XR. This R must be what? Alkyl group. Then they form RR. That is CH3 plus 2 NaX. If the reaction takes place like this, and this reaction R group consists of only alkyl group, then it is what? Here it is dry ether. Dry ether. Okay, that is Woods reaction. So in the place of R, I take the general reaction here. So R X plus 2Na plus XR gives rise to RR plus 2NaX. Listen here. If two R groups are alkyl, like CH3, C2H5, C3H7, etc., then this is Woods reaction. If R group is benzene or phenyl, okay, then it is Wittig reaction. Okay, next one R is alkyl, another R is alright, means benzene. Then it is Woods Wittig reaction. And already I gave you the reaction. Just go through with the video, then you will get. So at the same time, students, whatever the named reactions are there in these, you practice them, then you will get the good. Okay, and remember another two mechanisms are the conversion of ethanol to ethene, ethene to ethanol. You just prepare for those. Okay.